Welcome to this element of the lecture on air transfer, where we talk about thermal stack effect as one of the driving forces for air pressure differences within constructions and also within houses. The stack, or in Danish, skorsten, so skorstensvirkning, or the stack effect, or chimney effect, is the effect by which warm air, which is lighter than cold air, it rises with height. And that can then cause some pressure differences around the building envelope that can push air out in some places and draw it in other places of the structure, as we can see also through openings and such in the structures or in the house. So the reason is the difference or the temperature dependency of the air. And that means that if I go over here on the whiteboard, we can draw how the air pressure varies with height. And here we draw the air pressure. So down at the ground level, where we normally are, then the air pressure is 1 atmosphere or 101,325 Pascal. That is the pressure that is comes from the weight of all the air we have above us. So the air pressure will diminish with height, and we can draw it close to the ground or close to us. It diminishes almost linearly with height. That is the condition outdoors, where the density of the air at 0 degrees centigrade, if it's winter, for instance, at 0 degrees centigrade, well, then the density of air is 1.293 kilograms per cubic meter. But if we have indoor conditions, it's warmer, so the air is lighter, and then the way that the air pressure diminishes with height will be not as much as in the outside air. So there will be a slighter, diminishment of the air pressure outside, and this we can calculate by considering the density of air outdoors. So 20 degrees. Sorry, indoors, of course, 20 degrees as we have inside means that the air density is 1.205. So warm air is lighter or has a lower density. Now, going back to what we have over here, we have the formula that expresses how the air pressure diminishes with height. But now we can also consider the density as a function of temperature using the gas law. And then we have to insert the gas constant for air, and the absolute temperature is what we insert for the temperature. PA is the air pressure, the 101,325 Pascal, as we talked about before. So that by this equation, we now know how the pressure I talked about before, how it diminishes with height. Now let's draw it again a little bit to be theoretical a little bit more. If we assume we have a wall, indoor conditions to the right of the wall where it's warm, and outdoor conditions where it's cold, well then again we can draw how the pressure varies with height. If we assume we have the same air pressure down on the ground level at height 0, well then we can see how the air pressure diminishes less inside than outside, so there will be a higher air pressure inside and outside, kind of pushing air outwards through the wall. And this pressure, we can try to look to the differences as we do over here on the right-hand part of the screen. So that would mean that air would flow out, but this building I've kind of shown a little bit of here cannot be realized because the air that flows out, it has to come into the building also somewhere, and it cannot come in down here in the bottom. So there is, with this drawing, a little bit a mass conservation problem. Where should the air come from? So now we make it more real for a building. I showed two different buildings. The one that I have on the drawing on the top, it has an opening in the bottom of the wall and a similar opening with the same area and same air permeability on top of the wall. So air can as easily come in as it can go out on the top, in the bottom. That means that the air pressure, where it's the same between inside and outside, it's in the middle of the height of the building. So we have a neutral plane, the same air pressure between inside and outside in the middle of the building. If we have a similar building, but only with a twice as big opening in the bottom of the wall, well, then it's more easy to have air pressure contact in the lower parts of the building. And that means for my other building here, then the neutral height will be below the middle of the building, so it will be lower than what we saw from the other building. So this neutral height tells us about the level over which, when we are above the neutral plane, then air will exfiltrate through our walls, and when we are below, air will infiltrate. So this we can use to consider these air exchange and air circulation issues. And here is the formula by which I can calculate differences in air pressures between inside and outside, depending on where I am in terms of height, compared to the reference height, the neutral plane height. Now, also I should just finally just show that if we have a roof, because before I talked only about walls, but roofs, they are on top of our buildings, so very often we see exfiltration of air because we are above the neutral plane for that. Finally, I'll complete with a small example. It's a roof structure, so now it's only the structure where we have air circulation. It's an insulated roof, so it's cold on the outside. We have 5.85 degrees centigrade cold on the roofing outside of the insulation. And inside of the insulation, we have a small cavity here where it's 30 degrees centigrade. So air in this cavity will be lighter than out here. So here it's more heavy, here it's more light, so we have possibilities for air circulation around the insulation as illustrated here. So air will flow down on the outside and up on the inside, driven by the stack effect. So how much is the stack effect? Well, let's remind us about the formula. Well, the pressure varies with height, and its temperature dependency I've repeated here in the red frame. Now I'll insert the values for those temperatures that we had. At this, I'll take this formula, and I'm looking to the differences between cold and warm conditions, so the interior and the cavity conditions. So here I should insert those absolute temperatures. The rest we have from before in our formula. So if I insert numbers in absolute temperatures, of course, then altogether we get an air pressure that drives this circulation, which is almost 3 Pascal. It doesn't sound like much compared to the atmospheric pressure, which was 101,325, but it's a air pressure difference that continues to be there as long as we have the temperature difference, and enough that we can calculate hydrodynamically how much air circulation this will cause. So therefore, it's significant to be able to make these calculations of stack effect, although they may look like being small pressures. So thank you for listening to this description about stack effect in buildings.